Nous procéderons à une séance de questions. Vous avez 45 minutes pour faire cette présentation et vous pouvez commencer dès que vous êtes prêt.
Merci. Est-ce que je peux commencer par vérifier que la membre du jury qui est à distance m'entend bien? Je vais juste attendre qu'elle réponde. D'accord. Ok, je vais commencer. Merci. So thank you everyone for coming here today. I remove the mask. I will be presenting you my thesis work, which is about the automated verification of systems code using type-based memory abstractions. So as you know, software is taking a bigger and bigger place in our lives, to the point that many critical systems depend on it, including power plants, airplanes, and many sensitive information systems. Unfortunately, software still contains bugs and vulnerabilities, and new bugs are discovered regularly. To take just one example, as recently as last year, a bug was discovered in the Linux kernel, which allowed an attacker to perform an out-of-bounds write, which in the end of the process allowed the attacker to gain kernel privilege, which allowed them to do pretty much anything with the system. So this illustrates the fact that a bug in a kernel in particular can have dangerous consequences, and this is due to the particular role of the kernel in computer systems. So the operating system kernel is a program which organizes the sharing of hardware resources between applications. These resources can be the processing power, the memory, or input-output devices. And the kernel also has the role to prevent applications from disturbing each other by erasing another application's memory, for example, and it also has to ensure the confidentiality of their memory. And two bugs are particularly threatening in the context of safety and security of such systems. The first one is runtime errors. So if in the code of your kernel you encounter division by zero, for example, or an illegal memory access, then the kernel will crash, which may crash the whole system. And the second such kind of bug is privilege escalation, in which one of the tasks bypasses kernel protections and compromises the kernel, which in turn compromises the whole system. So due to the particular role of kernels in systems, it's particularly desirable to verify the absence of such bugs using formal methods. To see how this can be done, we need to take a closer look at how systems that use kernels work. So such a system, after running some boot code, will alternate its execution between the user code, so the code of the applications, and the kernel runtime. And the kernel runtime may do various things, but notably, it may pause the task that is currently running and run another one. To do this, the kernel needs to maintain some data about the tasks that are currently running. So to illustrate here, I will assume that this data takes the form of a linked list, more precisely a circular list. And each task object contains a pointer to the next task. And in addition, each of these objects contains a context. The context contains the values of hardware registers at the time the task was interrupted. And finally, each task object contains information for the memory protection of the task. So how does memory protection works on such systems? So for example, typically on embedded systems, you will have a hardware component called the memory protection unit, which controls access to memory by restricting memory accesses to an authorized interval of memory addresses. And this authorized interval is described in a structure stored in memory called the memory protection table. And you will have a special register, let's call it MPU, which points to such a memory table. And the memory table contains the start and end addresses of this authorized interval. And the idea is that only the kernel should be able to modify the memory protection configuration. And this can be done using a privilege level. So for example, you will have another special register called privilege, which contains 0 for unprivileged mode and 1 for privileged mode. and the MPU register can only be modified if the privilege equals 1. Now, to verify that these mechanisms are used correctly by the kernel and to verify the absence of runtime errors, we will need to verify invariance about memory. To see this, let me illustrate with a very minimal example kernel. So this function will be executed regularly, and what it does is that it first saves the context of the task that was just interrupted by writing into the address cur. So cur is a variable that points to the data of the currently running task. Then it will switch to the next task by following the next field. And then it will load the new memory protection for this next task by modifying the MPU register. And then through operations that, for simplicity, I don't detail here, it will restore the context of this next task and give control of execution to that task. Now, what kind of properties, what kind of invariance do we need to verify to check that this code does not have runtime errors and that the kernel remains protected? Well, for example, we need to ensure that cur does not point to a memory table or into a memory table, because if that was the case, when the kernel writes into cur, it may erase or corrupt the memory table in unexpected ways. So we want to ensure that this does not happen. We also want to ensure that at the end of this function, the memory protection is such that the kernel will be protected from the user code. A sufficient condition for this would be that the start address of the authorized interval at the end of the function is greater than the greatest address ever used by the kernel. This would be sufficient. And of course, the tasks must run unprivileged. So this translates to the fact that in the context of the task, the privilege register should be 0. Now, there are various techniques and methods to verify this kind of invariance on programs. Two such techniques are interactive proof and deductive verification, which consist in using either a proof assistant or an SMT solver or both to verify facts about the program. And these techniques have been used to verify strong properties on kernels before. However, they require a lot of work from people who are experts in both low-level programming and formal methods, which can be a problem, especially in embedded kernel development, where kernels are typically produced in many variants, depending on the hardware or the applications to run. And the companies that produce them don't necessarily have the means to perform verification for each variant or for each new version of the kernel. For these reasons, another line of work, sometimes called push-button verification, has arisen, and it's actually a variant of deductive verification for kernels which have a finite number of execution paths. And it's more automated. However, it still requires to write the kernel invariance manually, and these invariants can be pretty big. And another restriction is that such techniques only support bounded loops. Loops whose number of executions can be bounded statically, which is a problem for a number of features such as priority scheduling, which are necessary in real-time systems, for example. And finally, these techniques impose a fixed memory layout on the system, which has the consequence that the verification is performed for a fixed number of tasks, for example. So to try and push these boundaries, during my thesis, I explored an alternative approach, namely static analysis by abstract interpretation applied to the kernel executable. So static analysis by abstract interpretation have been used and applied to many problems successfully before with software such as FromSC or Astray. And we use such a static analysis on the machine code of the kernel to infer the kernel invariance. And this will allow us to handle unbounded loops and parameterized verification, so verification independently from the tasks, all this with a low annotation burden. And we will evaluate this approach on the Asterios industrial kernel. But first, so in what consists static analysis by abstract interpretation? Well, since the semantics of a program cannot be computed exactly in finite time, in general, abstract interpretation consists in computing what's called an abstract semantics, which over-approximates the concrete semantics of the program. So to illustrate, suppose that we want to verify numerical assertions on this program. A very simple way to abstract numerical variables in abstract interpretation is to use intervals. So for example, if x and y take a random value between 1 and 4, then this can be abstracted by the interval 1, 4. And then using interval arithmetic, we can deduce that z is necessarily between -3 and 3. And still using the same kind of reasoning, we can automatically deduce that r is between -9 and 9. And this allows us to verify the assertion that r is necessarily less or equal to 9. However, because this interval contains all the values of r but is not necessarily exact, we are not able to prove that r can be is always non-negative. And this is an example of a false alarm, because here in reality r is always non-negative, but with this simplistic abstraction we were unable to prove it. We would have to use a richer abstraction for this. Now coming back to memory analysis, there are two main kinds of memory static analysis, pointer analysis and shape analysis. Pointer analysis infer points to relations or aliasing relations between variables of a program. So some of these analyses, for example, infer statements of the form x can point to either y or z. And they are usually very efficient and are heavily used in compiler optimizations, for example. But in addition to being difficult to apply to machine code, they do not consider the reason about the structure of data in memory, nor about its values in memory, which has a consequence that on our example kernel, for instance, we wouldn't be able to deduce interesting facts about the possible values of cur or NPU with a pointer analysis, because it would have to reason about the structure of the data pointed by cur and NPU and about its possible values. So this is not adapted for our needs. Shape analysis, on the contrary, can verify strong properties on memory. To illustrate, I take the example of a shape analysis based on separation logic. At the top, you have an abstract state, and at the bottom, you have an example of a corresponding concrete state. And so such a shape analysis will be able to verify properties such as cur points to a circular list of tasks, or NPU points to a structure with two fields, and the first field is greater than kernel last address. And in addition, it will be able to verify that all these objects are separated in memory. So these strong invariants would suffice for our needs, but there is a number of difficulties. Shape analysis have seldom been applied to low-level code and not yet to machine code, but more critically, to verify those strong invariants, shape analysis perform case disjunctions during the verification, and the number of disjunctions can grow very large, which can be costly. Also, the separation constraints can make some forms of sharing difficult to express. And finally, shape analysis can be sensitive to precision loss, in the sense that a small imprecision during the analysis may render the analysis unable to prove anything about the rest of the program, which can be a problem when you want your analysis to be as automated as possible. Which is why during my thesis, I explored a different form of invariance, namely memory invariance based on types. For that, I developed a type system called physical types, which describes the layout of values in memory. For example, the type defining a memory table would be defined as a product type. So product types encode contiguous values in memory. So the two contiguous fields here. And then to express the fact that the first field must be greater than kernel last address, we can use a refinement predicate to express this numerical constraint on the value. Similarly, for the context type, the context of a type can also be a product type with a refinement predicate to express the fact that the privilege field should always be 0. And the task type is a bit more complex. It uses pointer types. So in physical types, a pointer type may specify an offset into the pointed type, but here the offsets are simply 0. And so a task is a pointer to a memory table, followed by a context, followed by a pointer to a task, which must be non-zero. And the invariants expressed by this type system are weaker than those expressed by shape analysis, in the sense that objects of the same type are not necessarily separated. So you may end up in the situation at the top with a well-formed circular list, but you may also end up in one of the two other situations. For example, all the tasks may point to the same memory table, or you may have two disconnected linked lists, or you may even have an ill-formed linked list with a cycle at the end, like this. But we will see that this kind of invariant already suffices to verify the properties that we need. And we do have some facts about separation in this type system. For example, a task and a context may alias. They may live in overlapping regions of memory because a task contains a context. But a task and a memory table, for example, may never alias. So you have the fact that if alpha is of type pointer to task and beta is of type pointer to memory table, then alpha is different from beta. And using this, we will be able to verify, as I said, the kind of things that we need. So suppose we start from a situation where cur is a pointer to a task and is non-zero, and MPU is a pointer to a memory table. Then we can verify that when the kernel writes into cur some data, then this is safe and this does not modify any memory table because there is no aliasing between tasks and memory tables. And then switching to the next task modifies the value of cur, but the type invariance allows to verify that it remains a pointer to a task and it remains different from 0. And modifying MPU, still using the type system, we can verify that MPU remains a pointer to a memory table. And then this last line does not modify these two invariants. And since we have encoded in the types the fact that the kernel will be protected from application code, we will be able to verify the properties that were of interest, so absence of runtime errors, but especially absence of privilege escalation. So I will, during my presentation, detail the components of this verification, starting from this type-based memory abstraction, which encodes structure invariance on memory as a form of type safety. And we will see that in a number of common situations, we have false alarm. So to improve the precision, we have to use another abstraction, which I call points to predicates. And based on this memory abstraction, I implemented two low-level static analyses, one for C and one for machine code. And using the machine code analysis, I developed a method to verify absence of runtime errors and absence of privilege escalation, on embedded kernels, and applied it to an unmodified industrial kernel. So starting with this memory abstraction, to give meaning to physical types, one thing we have to do is to label memory with types. So suppose we start from this untyped memory with a linked list containing two elements. The first thing to do is to define a set of physical types that are suitable for this data. So on the left here, you have example C types that could be used in a C program, but in the middle, you have physical types, which is a richer type system. And so the list type is a pointer to a list, followed by a data, and the data is simply the type word4, word4 being the type for any value of size 4 bytes. And then the memory can be labeled with types to specify here that the two regions in pink are of type list. Then the analysis operates on a low-level language similar to an assembly language with memory operations, but also variables. And for example, suppose that here we have two variables, and the variable L points to the head of the list. Then the instruction N is assigned the value stored at address L, causes N to point to the second element of the list. And then the instruction store in N the value of L makes this list circular. So this language can be given a type semantics by, as I said, labeling memory with types, but also the variables. So here, for example, initially L is a pointer to a list, and N is of type word4. The first instruction will modify the type of N in this type semantics. So N becomes a pointer to a list. And the second instruction does not modify the types. It only modifies the values in memory. And essentially how the type-based analysis will work is that it will abstract away the memory and keep only the types of variables. The memory is abstracted by the fact that the type invariance should hold. And using this, the analysis will be able to verify the safety of operations. Now, this wouldn't suffice on its own. We also need to represent some numerical predicates in the analysis. Numerical predicates are necessary to verify the non-nullness of pointers, but also the manipulation of array indices and pointer arithmetic, and to use and verify the refinement predicates that may be present in the types. So to achieve that, we use a numerical abstract domain in combination with our type-based abstraction. And any numerical abstract domain may be used. I mentioned the domain of intervals in my introduction, but a much more sophisticated domain can be used. So to express the fact that we have numerical predicates in the abstract state, I will represent them on the right here, with numerical formulas. And so here, for instance, this abstract states expresses that L is a pointer to a list and is different from 0, and that N is any 4-byte value that is lesser or equal to 10. With this abstraction, we are already able to analyze a broad range of programs. To take just one example analysis, suppose we start from this initial abstract state, and we want to retain the condition. So we assume the condition that L is different from 0. This is retained by the numerical abstract domain, and then the analysis is able to verify that dereferencing L is safe because L points to a list and is different from 0. And as a result, N is now a pointer to a list as well, which is the type of the first field of a list. So I verified the soundness of this abstract semantics, which is represented here at the top edge. So the abstract semantics maps an abstract state to another abstract state, and an abstract state represents a set of typed states through the concretization function gamma. And then at the bottom, you have the concrete semantics, which operates on sets of concrete states. And in addition to this soundness theorem, we have the fact that the analysis verifies that the program preserves the typing invariance. Now, as I said, this abstract domain already allows us to analyze a broad range of programs, but there's still a number of situations where we have false alarms. So for instance, suppose that we want to assume the condition that that the value stored at L is non-zero. Well, since the memory is not represented explicitly by this abstraction, the abstract state cannot represent this fact, cannot retain this condition. And as a consequence, the analysis will not able to verify that dereferencing L twice is safe. So to remedy this, and taking inspiration from shape analysis, which can increase or reduce the precision when needed, what we do is that we materialize the corresponding memory region in what's called a points to predicate. And so here, this abstract state expresses the fact that L points to a memory region with two fields, and the first field is non-zero. And so having retained this fact, the analysis is able to verify that dereferencing L twice is in fact safe. Points to predicates are also useful in another common situation, namely the temporary violation of the typing invariance, the structure invariance, which often happens when you want to initialize data structures. So suppose we want to allocate a list node and then initialize it. What should be the result of this allocation operation? It would be incorrect to say that L now points to a list because it points to uninitialized memory. And this uninitialized memory does not necessarily comply with the invariance of the type list. It would be correct, but imprecise, to say that L now points to any value of size 8 bytes. So it's not satisfactory because we have lost the fact that L points to a list. So what we do is we say that L points to a list, but we add a points to predicate to represent the fact that L points to an unknown value of 8 bytes. And with this, the effect of the next two instructions can be represented more precisely. And so here, for example, the analysis will be able to verify that after this, the materialized region does verify the invariance of a list. And then if needed, the analysis can drop this points to predicate, and it has soundly inferred that L is of type pointer to a list. So yeah, these points to predicates allow us to avoid a number of false alarms. Based on this abstraction, I implemented two static analyses, one for C and one for machine code. So the common parts are implemented into the codex library, abstract interpretation library, developed at CEA in OCaml. And the C analyzer is implemented as a module of from a C. which is a modular platform for the analysis of C code, also developed at CA. And for the experiments, I instantiated the numerical abstraction to intervals with congruence information in combination with a bitwise abstraction to remain precise on bitwise operations such as bit shifts or masks and the like. All this in combination with a domain of symbolic equalities and inequalities. The machine code analysis has similar ingredients, but it's implemented as a module of BinSec, the binary analyzer, also developed at CA. And BinSec takes care of decoding machine code instructions into an intermediate representation, which allows our analysis to operate on executables for various architectures, such as x86 or ARM, for example. An adaptation has to be made for the memory abstraction, because the type-based abstraction was not relevant, was not precise enough to use for the stack and the global data, because especially for the stack, the same memory location may hold many different values over time. So a type-based abstraction is not adapted. So I used what I call an array of bytes abstract domain, which maps numerical addresses to abstract values, and the type-based abstraction for the rest of memory. And finally, for the machine code analysis, as you know, control flow is not explicit in a binary program. It depends on the possible states of registers and memory because of dynamic jumps. So the analysis has to infer simultaneously the possible values and the possible control flow. So I implemented this and formalized it as an abstract domain and verified that the resulting control flow graph does contain all the possible executions. I evaluated these two static analyses on a number of benchmark programs from two shape analysis papers, so by Li et al. In 2015 and Li et al. In 2017. And these programs contain complex data structure manipulation with structures such as AVL trees or various types of lists, but also union-find data structures and graphs, which are challenging even for shape analysis. And we analyze so all the programs from these two papers, 34 programs between a few dozen and several hundred lines of code. And the property that we wanted to verify was the preservation of these structure invariants and the spatial memory safety. Because in fact, the fact that the program preserves these structure invariants implies spatial memory safety. That is the fact that all memory accesses are made within the bounds of a valid object. And we evaluated the analysis time and precision in terms of number of alarms and the number of annotations that are necessary. The process is the following. First set of physical type definitions can be generated automatically from the C types. And then those physical types can be refined if necessary. And by refined, I mean that you can add type predicates or specify the length of arrays. And then you can run the analysis. And if there are false alarms, the types can be refined again if necessary, until hopefully the analysis completes without alarms. So the source code, the C analysis was applied to the source code, and the machine code analysis was applied to the compiled executables at 4 different levels of optimization. The first result was that the annotation effort necessary is rather low. It varies between no annotations and 12 lines of annotations. And the mean annotation code ratio is 3.2%. And in terms of precision, we were able to verify the property on 30 out of 34 benchmark programs, both in C and on the machine code at all levels of optimization. We also found that the points to predicates are necessary to the analysis in the sense that if you disable them, then the number of successfully verified programs drops significantly. Finally, in terms of analysis time, so all these analyses complete in less than 1 second, but then I wanted to evaluate the hypothesis that we benefit from not having to represent case disjunctions. So I reproduced the experiment by Li et al. In a 2017 paper, where they analyze a program which performs 32 insertions into an AVL tree. And this program is challenging for shape analysis because of the potential number of case disjunctions. And we see that our analysis, without any adaptations, obtains comparable runtime to a shape analysis with guided clumping. Guided clumping being a technique to keep the number of disjunctions under control during the shape analysis. So, of course, the shape analysis verifies a stronger property than we do, as I said in my introduction, but this suggests that type-based invariants allow us to easily keep very predictable runtimes. Now, coming back to kernels, I applied the machine code static analysis to embedded kernels to verify, if you recall, absence of privilege escalation and absence of runtime errors. And this analysis is automated. So not only because using sound static analysis by abstract interpretation allows us to infer the kernel invariance, but we also will use the fact that absence of privilege escalation, as we will see, is an implicit property. And by that, I mean a property that does not require to write a specification. So applying it to the machine code allows us not to rely on the compiler. And the verification is parameterized in the sense that it does not depend on the tasks. And finally, we evaluated it on an unmodified version of the Asterios real-time kernel, as well as a few other experiments. So I introduced the notion of implicit properties. An implicit property is a property that does not depend on a particular program. It only depends on the semantics of your programming language. So for instance, absence of runtime errors is an implicit property because it can be phrased as the fact that you never reach some error state. And the notion is interesting because an implicit property can be verified by the same static analysis on many different programs without the need to write a specification that is tailored to each program. And we will see that absence of privilege escalation, is an implicit property. But to see this, we need to take a new look at the system. If you recall, the system alternates between the execution of user code and the kernel runtime. And we have applied the machine code analysis to this entire system loop. So it's called the system loop. But the user code is unknown. Only the kernel code is known at the time of the analysis. So what we do is that we abstract the user code by arbitrary sequences of instructions, effectively giving more power to the applications and to a potential attacker. But those arbitrary instructions are still limited by the hardware protections, so memory protection and the hardware privilege level. And the fact that absence of privilege escalation is an implicit property is given by this theorem, namely that if the system satisfies a non-trivial invariant, so in this case, any state invariant, different from always false or always true, then the system is immune to privilege escalation. And the proof is quite simple. If the system is vulnerable to privilege escalation, since we have assumed that the attacker may do anything permitted by the hardware, then the system may reach any state. And as a consequence, the only invariant that holds on the system is the trivial invariant, true. And a consequence of this is that absence of privilege escalation can be verified, perhaps surprisingly, without writing a specification. To see this, let me illustrate in a situation where everything is known about the data of the tasks. For example, suppose we start in a situation where cur is a known address and NPU is also a known address. Then a simple analysis can establish very basic facts. For example, writing into cur does not modify the values of cur or NPU. Then switching to the next task will modify the value of cur. Then NPU is updated, but here for simplicity, I assume that both tasks use the same memory protection table, so at the same address. And then this last function does not change these two facts. And then the user code has control. And the user code may do anything, but within limits of hardware protections. And so supposing that the memory protection table here ensures kernel protection, then the analysis can verify that kernel memory is untouched by the user code, and in particular, cur and NPU are not modified. And as a consequence, nothing changes about them during the execution of user code. Only now the analysis discovers that cur may have another possible value. So it will propagate this fact down this function. And now the analysis has reached a fixed point, which means that this is an invariant of the system. And by the previous theorem, this system is therefore immune to privilege escalation. So what this shows is that absence of privilege escalation can be verified on such very simple kernels without any annotations at all, and absence of runtime errors as well, which is an interesting fact, but of course, it's not quite what we wanted, because this verification was not generic. We wanted to analyze the kernel independently from the applications, and here it was not the case. It's also probably not scalable in the sense that if you have 1,000 tasks in the system, then the analysis would have to enumerate 1,000 addresses, which is costly. And so, as I said, the key idea is that we use the type-based abstraction to represent the data of the tasks. And so here are our kernel types again. And I've already walked you through the analysis of this code earlier, so I will not detail each step again, but I haven't told you about the effect of user code. So here, since we have encoded in the types the fact that the kernel memory is protected and the fact that the task is not privileged, the analysis is able to verify that the user code will not modify kernel memory, and so it will not modify cur or MPU. And so, as a consequence, in one more iteration, the analysis will be able to verify that this is in fact an invariant of the system, which means that this system verifies absence of privilege escalation. So we have here a more generic and more scalable way of verifying absence of privilege escalation. One last difficulty with this approach is that the type-based analysis is good at verifying the preservation of invariants, but sometimes in a kernel, the boot code establishes some of these invariants, and this is much harder to verify. So what we do is we perform a parameterized analysis of the runtime, so you're using the type-based abstraction, and an in-context analysis of the boot code, and we check that the state after boot matches the typing invariant. And this way, we are able to verify the entire kernel. So I evaluated this methodology on the Asterios microkernel, which is used in the industry. So it's a kernel for the ARM architecture. Its executable consists in about 10,000 instructions, and it's protected using page tables, which is a protection mechanism which is more complex than what I used in my examples, but the essential principles are the same. And due to a limitation in the current design of physical types, we had to assume that all stack sizes are the same for all of the tasks, which is the default setting. And then in the first beta version of the kernel, we found one vulnerability, which was due to improper sanitization of a system call number. And then in a V1 version of the kernel, where this vulnerability was fixed, we were able to prove absence of privilege escalation and absence of runtime errors in 430 seconds. And we only needed 58 lines of annotations. Then to evaluate the genericity of this approach, I analyzed a completely different kernel. So EducaTOS is a small OS developed for teaching purposes here at CEA by Mathieu Lemaire and I. And it's a separation kernel with some real-time scheduling algorithms, and it permits dynamic thread creation. Its executable has a bit more than 1,000 instructions, this time for the x86 architecture, and the memory protection mechanism is segmentation. And we were able to verify absence of privilege escalation and absence of runtime errors on 96 variants of EducaTOS, the varying parameters being the compiler used, or the optimization flags, or the scheduling algorithm, for example. And the verification time ranged from a bit more than a second to 73 seconds. And we and we needed no more than 14 lines of annotations. And then finally, I wanted to evaluate the hypothesis that the in-context analysis can verify some kernels without annotations, but does not scale. So what I did was analyze the same variant of EducaTOS with the in-context analysis and the parameterized analysis, so the analysis using types, with varying numbers of tasks. And the result was that the time and space complexity of the parameterized analysis is almost linear, whereas the complexity of the in-context verification is quadratic, which makes it impractical from about 1,000 tasks. So I'm going towards my conclusion. During my thesis, I developed a type-based memory abstraction, which I presented you, which allows to verify structure invariance on memory as a form of type safety. And I complemented it with points to predicates to improve the precision without introducing disjunctions. Based on this, implemented two low-level static analyses, one in BaseSec and one in pharmacy, to verify the preservation of those structural invariants, which notably implies spatial memory safety. And I think this is notable because violations of spatial memory safety is still among the first causes of software vulnerabilities. And these analyses are less precise, but also more easily applicable than shape analysis. And based on them, I developed a method to verify absence of runtime errors and absence of privilege escalation on embedded kernels. The perspectives for future work that I see starting from this go in two directions. The first would be the collaboration with other proof methods, because other techniques such as program proof or deductive verification verify possibly stronger properties than we do, or more properties. But using them, establishing the invariance can be quite costly, especially on kernels, especially in machine code. This has been noted by the people who verified the SEL4 secure kernel. And so I think it would be interesting to use the facts inferred by our analysis, such as, for example, in machine code, the control flow graph, or the possible program states at every program point, as an input to other verification tools. And a second direction would be to enrich the type system to verify stronger properties. Because one interesting point with this analysis is that when you modify the type system in a certain way, you get sort of for free new static analysis. And so one interesting direction in that way would be, I think, to taking inspiration from dependent type system to add types that are quantified by values. And this would allow us to express things such as arrays of dynamic size, or it might allow us to verify non-interference or isolation between the tasks, and not only protection of the kernel from the tasks. And I know that Julien Simonet is currently working on this for his PhD. Another interesting direction would be to combine the type-based invariance with separation logic to express local separation constraints. So, for example, express that in a binary tree, in the type of a binary tree, the children node are separated from each other and separated from the parent. This would allow the analysis to be more precise on the aliasing relations, which would allow to gain precision in all the rest of the analysis and possibly progress towards the verification of stronger properties, such as, for example, temporal memory safety. So yes, thank you for listening, and I'll be happy to take your questions.